Hey gang, welcome back to 4600. We're going to go over the 5.7 recommended homework solutions today, and I'll parse them out in like I've been doing so that you don't have to watch them all if you don't want to. The first one at 5.89 says that in exercise 5.1, which we've done before in the past, we determined that the joint distribution of y sub 1, the number of contracts awarded to firm A, and y sub 2, the number of contracts awarded to firm B, is given by the entries in the following table. So we've seen this table before. Matter of fact, we had to find it back in chapter 5.2. So it says find the covariance of y sub 1 and y sub 2. Does it surprise you that the covariance is negative? And why do you think why or why not does it surprise you, I guess? I think that's just kind of a silly question in this case because we don't know, but they're telling us it's going to come out negative. So we're going to go ahead and do the expected value of y sub 1 times y sub 2, which we know from the covariance formula we need. And we're going to go through and start multiplying each random variable value times its probability, and that's what we're going to do. So we got 0 times 0. Write that a little bit better. 0 times 1/9 plus next one's going to be 1 times 0 times 2/9 plus, and we just keep going that way. Next one's going to be 2 times 0 times 1/9 plus, now we go 0 times 1. I'm doing second row basically with the y sub 1 values. 0 times 1 times 2/9 plus 1 times 1 times 2/9 plus 2 times 1. I made it an order pair. Old habits. Times 0. That's the probability there. And then I'm going down to the last row and doing it with y sub 1 values. So that's going to be 0 times 2 times 1/9. And the rest, these other two should zero out. We got 1 times 2 times 0 plus 2 times 2 times 0. And when you go through that, you're going to find out that everything cancels or just basically goes away because most of these are zeros, and you're left with just 2/9 as your expected value of y sub 1 times y sub 2. The expected value of y sub 1 is going to be basically taking the column the discrete value for the random variable y sub 1 and multiplying it times its basically we're going to be doing the times the marginal distribution of when y sub 1 equals 0, which is just summing up the column there, and that becomes 4/9 the probabilities do. So we get 0 times 4/9 plus 1 times 4/9 plus 2 times 1/9 is the last column there, and this cleans up to be just 2/3. And to kind of, so I don't bore you here, you'll get the same thing if you do the rows. You should do 0 times the rows total, which is for the probabilities, which would be 4/9. 1 times the second rows sum, which is 4/9 for the probabilities, and then 2 times 1/9 there. And so what you'll end up getting there is the same thing. So you get the same thing for y sub 1, the expected value of y sub 1 and y sub 2. And so the covariance of y sub 1 and y sub 2 is equal again to the expected value of the y sub 1 times y sub 2 minus expected value of y sub 1 times the expected value of y sub 2. And so just plugging in our good old numbers there, we got 2/9 minus 2/3 times 2/3, which should give us negative 2/9. And so it is indeed a negative covariance. And that essentially tells us that as the value of y1 increases, the value of y sub 2 tends to decrease. All right, so what does that tell us? That tells us that when value of y sub 1 increases, the y sub 2 decreases. All right. And that's kind of the reason why we shouldn't be surprised. And it's kind of harder to see that with this table of probabilities. I mean, we don't have data at our hand so we can see a scatter plot like we did in lecture, where we can see the obvious increase of y sub 1 and y sub 2 decreasing on average. But looking at the table real quick, what they're basically saying is as y sub 1 gets bigger, and concentrate on the probabilities there, as the actual value, the random variable actually increases. It's not talking about, we're concentrating on the probabilities, that the probabilities tend to decrease. So larger values of y sub 2, typically we find the probabilities decrease. The bigger y sub 1 is, the smaller the probability is for when you've got the y sub 2 variable in tandem. So it's kind of a weird excuse there. I don't really like this question per se. I mean, like that question of why are we surprised? We didn't have it calculated yet, so we wouldn't have been surprised one way or another. But ultimately, the probabilities in this problem here are what dictated us getting that negative covariance in the end of things. So don't worry too much about that. But we should note that negative 2/9 covariance tells us something. If we go back to think about theorem 5.11, which said that if y sub 1 and y sub 2 are independent, and we know they're independent, then the covariance must be 0. And then the contrapositive of that statement is true here. So if the covariance is not equal to 0, in this case it's not, then we can assume that the random variables are dependent. And we could show that they're dependent using the rules we've learned before, but this is another way to say that this also tells me that y sub 1 and y sub 2 are dependent. Okay, so let's do the next one next. So the next one's exercise 5.90. And we've seen that we've worked with this problem back in a couple of times as well. So in exercise 5.3, we determined that the joint probability distribution of y sub 1, the number of married executives, and y sub 2, the number of never married executives, is given by the following probability function, or really a multinomial function, where y sub 1 and y sub 2 are integers and y sub 1 is between 0 and 3. Y sub 2 can be a value between 0 and 3. And then y sub 1 plus y sub 2 has to be some value between 1 and 3. They ask us just to find the covariance. So recall in this one, they were picking 3 individuals out of the 9. And so that's where the formula came from. We're not going to go through that whole rigmarole again. I've got the table set up already for us with the probabilities ready to roll, so we don't have to mess with that this go round. We're actually going to end up, do you think we're going to get a negative covariance here, just looking at the table? Based on the last example, it seems like that would be the case, right? We've got a lot of zeros down when y sub 1 and y sub 2 are both large values, around 2 and 3. We get a lot of zeros down there, so it seems like the covariance is going to come out to be negative here. And so again, we need to find expected value y sub 1 and times y sub 2. And this is a much larger one here to deal with, so definitely be careful with it. But we end up getting 0 times 0 times 0. We could just write that as 0 up front. Plus 1 times 0 times 4 over 84. Plus 2 times 0. You know what? I'm going to cheat this real quick and just go through it like this. This probability is going to be gone. This one, and this one, because they're in the 0th. The column value here is 0, so that'll cut those all out. Because this row is 0, we're going to cut these guys out. Because there's a 0, anywhere there's a 0 is automatically going to cancel out because it's not going to add anything to our probability. So we really need to concentrate on those 3 middle guys there, and what they multiply out to. So we end up getting for the 24 over 84, it's in the one column, one row, so we get 1 times 24 over 84. Plus the next one, the 18 over 84, is in the 2 1 column, so it's 2 times 1 times 18 over 84. Plus the 12 over 84 is in the 1 2 column, so we get 1 times 2 times 12 over 84. And somehow, and low and away, if we multiply those out, that would just be 24 over 84. Plus 2 times 18 would be 36 over 84. Plus we'll get 2 times 12, which is another 24 over 84. 24 over 84. And that sums to 1. So our expected value of y sub 1 times y sub 2 is just sums out to 1, which is kind of a nice number, surprisingly. Expected value of y sub 1, though, we calculate by doing the column discrete values times the sum of the probabilities in that column. So I should get 0 times, this should be 10 over 84, plus 1 times 40 over 84, plus 2 times, it's like 30 over 84, 30 over 84, plus 3 times 4 over 84. And this one turns out to simplify down to 4/3. The expected value of y sub 2 is just us doing the rows this way. So I'm concentrating on the rows this time, and then the row totals. So for expected value of y sub 2, that's going to be 0 times, and this one you got to be careful with because it's not going to be the same. 20 over 84 plus 1 times 45 over 84 plus 2 times 6 and 12 is 18 over 84 plus 3 times 1 over 84. And I won't simplify that down, I'll just give you the final answer there. That's 1. So the covariance here of y sub 1 and y sub 2 is equal to 1 minus 4/3 times 1, which just equals negative 1/3. So not surprisingly, again, we got another negative covariance. Obviously, this we kind of look at the table at this point and say, yeah, they're y sub 1 and y sub 2 are dependent upon each other, and getting a negative value once again says that if as y sub 1 increases, y sub 2, the variable y sub 2 tends to decrease. So similar thing there. All right, so let's get on to the next one. All right, exercise 5.91 is a continuous case. And it says in exercise 5.8, we derive the fact that, because we had to find the value 4 there, that 4 y sub 1, y sub 2, for y sub 1 between 0 and 1, and y sub 2 between 0 and 1, and 0 elsewhere is the function of y sub 1 and y sub 2. Show that the covariance equals 0, and it asks us, does it surprise you that the covariance of y sub 1 and y sub 2 is 0? And again, why? So another one of those surprise questions. This one's a little easier to answer, and because we've done something with this problem in an earlier exercise. So I will do all the work over here, because again, we need to find the expected value of y sub 1 times y sub 2, which is going to be the double integral. And since we have separated y sub 1 inequality versus y sub 2 inequalities between 0 and 1, we can just assume that we're going to do that. And we're going to multiply into y sub 1 times y sub 2 times the original function that was given, 4 y sub 1 times y sub 2. And we'll just go y sub 1 dy sub 2 in that order. So always, like I do, I clean things up. 4y sub 1 squared, y sub 2 squared. All right, dy sub 1, dy sub 2. All right, so that's going to clean up and do the integral for the dy sub 1, or in respect to y sub 1 first. So we do that, 4y sub 2 squared is just a constant, and we get 1/3 y sub 1 cubed between 0 and 1 dy sub 2, which gives us the integral from 0 to 1 of 4/3 y sub 2 squared, and the y sub 1 cubed goes away because we're plugging 1 and 0 into it, or just becomes 1. So dy sub 2, and then we integrate this sucker, and we end up getting y sub 2 squared becomes y sub 2 cubed over 3, so this becomes 4/9 times y sub 2 cubed, evaluated from 0 to 1, so we find that this is 4/9. The expected value of y sub 1 we've already found in the past, so I'm not going to worry about going through that. I'm going to set the integral up for you and give you the final answer. But the double integral will be from 0 to 1, 0 to 1. We multiply in an extra y sub 1 times 4 y sub 1 y sub 2, and then can go in the y1 direction or y2 direction, whichever one you prefer first, equals 2/3. And lo and behold, expected value of y sub 2 is a similar scenario. Then you should have done a double integral between 0 and 1, 0 and 1 of multiplying in a y sub 2, extra y sub 2 variable there, times the 4 y sub 1 y sub 2, dy sub 1 dy sub 2, and that also actually equals 2/3. So the covariance of y sub 1 and y sub 2 is just equal to 4/9 minus 2/3 times 2/3, which does indeed equal 0. So they asked us if that surprised us. No, it doesn't. If you recall, this is one of the ones from an earlier lecture or homework exercise where we had to show that the function was independent. Also, that one rule that said if we can take f of y sub 1, or if we could break the function down into two parts where it's g of y sub 1, comma, something like f of y sub 1, y sub 2 could be described as a function of g of y sub 1, h of y sub 2, and that all depended upon these guys being separate like this. And we could definitely do that because remember we could get 2y sub 1 and 2y sub 2 and split them apart into two different marginal distributions, that these were indeed independent. And so it doesn't surprise me here. I'd say no, I'm not surprised. Because y sub 1 and y sub 2 are independent. And you could invoke that theorem if you wanted to, or what you really should do in the case of this is actually show that it's independent if you're going to use this. Because we already know they're independent from an earlier exercise. But if you didn't know that, you need to show that. But I'm just going to cop out here and say from an earlier exercise, because we've already proven that once. And so that's all there is to that one. Okay, so exercise 5.95 says, let the discrete random variables y sub 1 and y sub 2 have a joint probability function p of y sub 1, y sub 2 equals 1/3 for the order pairs y sub 1 and y sub 2 when they equal -1, 0, 0, 1, and 1, 0. It says find the covariance, and they also give us a notice that y sub 1 and y sub 2 are dependent and ask us why, and says this is another example of uncorrelated random variables that are not independent. So this is kind of like the very last example we did in 5.7 lecture. And so this is a case where we need to kind of show both things. So what that little ordered pair does, it says that p of y sub 1 y sub 2 equals 0 where, and they gave us the ordered pairs. If you want to think about that as a table, we got y sub 1, and the values for the y sub 1 variable in those ordered pairs were either -1, 0, and 1. And then the y sub 2 variables, we only had options of 0 and 1. So we can think about this as a table. And it said for -1, 0, I believe, 0, 1, and 1, 0, the probabilities of those ordered pairs was indeed 1/3. So this is 1/3 here, 1/3 here, 1/3 here, and everywhere else we get zeros. So we can do this much like we did the other problem. So the weird part about this was the setup of the problem and the way they gave us the information. But after that, this becomes very simple. So expected value of y sub 1 times y sub 2 is just going to be, it turns out it's just going to be 0, but -1 times 0 times 1/3 plus 0 times 0 times 0 plus 1 times 0 times 1/3 plus -1 times 1 times 0 plus 0 times 1 times 1/3, and then finally plus 1 times 1 times 0. But everything's got a 0 in it, so this just equals 0. Well, that was rather nice. The expected value of y sub 1 is just, again, the things we've been doing before, so it should be -1 times the first column's total, which is 1/3, plus 0, the random variable 0, times the 1/3, because that's the second column's total, plus 1 times 1/3 again. But this also turns out to be 0. So you're probably going, well, isn't that going to be what expected value of y sub 2 is? And don't always count on that. This is a weirder table than the ones we've seen before, or different. It's not as uniform as some of the ones we've dealt with. So this time we're doing the rows, so we do 0 times 2/3 plus 1 times the column, or the row total of the second row, which is 1/3, and so this just turns out the expected value of y sub 2 is 1/3. All right, so the covariance of y sub 1 and y sub 2 is just going to be equal to 0 minus 0 times 1/3, which is just 0 no matter how you cut it. So that's 0. But the thing is saying, and the thing the problem was saying is, notice that y sub 1 and y sub 2 are dependent, and asked why are they dependent. Well, it's not really so much a question of why here, it's just showing that it is. So we got 0, right? And then we said if the covariance equals 0, then they might have, usually if the two variables are independent, then the covariance equals 0. But in this case, we just need to show one case, right? So y sub 1 and y sub 2 are dependent because of the following. And there's more than one correct answer to show this here, but I'm going to choose p of -1, 0, and I'm going to show that it's not equal to p sub 1 of -1 times p sub 2 of 0, right? So p of -1, 0 is that very first probability here, so it's 1/3, and that's not going to be equal to p sub 1 of -1. So if we go, the marginal distribution of -1 is 1/3. The marginal distribution of p sub 2, 0, is the row total here, which is 2/3. And obviously those two things are not going to equal each other, so that's enough proof right there to say that they're dependent. Okay, and that's all there is to that one. All right, so the next one is 5.96, and it says suppose that the random variables y sub 1 and y sub 2 have means mu sub 1 and mu sub 2, and variance is sigma sub 1 squared, wow, that's a mouthful, and sigma sub 2 squared, respectively. Use the basic definition of the covariance of two random variables to establish the following. A, that the covariance of y sub 1 and y sub 2 is equal to the reverse of that, covariance of y sub 2 and y sub 1. Seems intuitive, right? And then B, show that the covariance of y sub 1 and y sub 1 with itself is equal to the variance of y sub 1, which equals sigma sub 1 squared. Basically, that is that the covariance of the random variable in itself is just the variance of the random variable. All right, so we're going to do that here on the next page. So part A, they want us to show that the covariance of y sub 1 and y sub 2 was equal to its flip-flopping the order, basically the ordered pair, if you will. So we start out there, and remember from the definition that was equal to the expected value of y sub 1 minus mu sub 1 times y sub 2 minus mu sub 2, which are just the the deviations of each value from the mean of each point for the y sub 1 and y sub 2 values. But remember, products are flip-floppable because it doesn't matter what order you multiply in, you're going to get the same solution, right, most of the time. And so we could rewrite this as y sub 2 minus mu sub 2 times y sub 1 minus mu sub 1, and just flip those around. And since multiplication is, I guess the term I want to use is associative, we can flip-flop it. Then this is just equal to the covariance of y sub 2 and y sub 1. So a pretty simple little proof. If I can draw a little box there. You know what, I'm going to do this. What some people do, the little triple sign or whatever. Part B, a little different. They want us to show that the covariance of y sub 1 and y sub 1 was equal to the variance of y sub 1. So if we take the covariance of y sub 1 and y sub 1, that's going to be equal to, based on the definition, the expected value of y sub 1 minus mu sub 1 times y sub 1 minus mu sub 1, which is really equal to the expected value of y sub 1 squared minus 2y sub 1 mu sub 1 plus mu sub 1 squared. Okay? All right, and so expanding that expected value symbol out, we get expected value of y sub 1 squared minus 2 mu sub 1 times the expected value of y sub 1 plus mu sub 1 squared, because the expected value of a constant is still a constant, which equals the expected value of y sub 1 squared minus, now the expected value of y sub 1 is just mu sub 1, so we get 2 mu sub 1 squared plus mu sub 1 squared here, which just equals the expected value of y sub 1 squared minus mu sub 1 squared. Well, mu sub 1 squared, it can be rewritten again to be the expected value of y sub 1 quantity squared, which looks an awful lot really familiar to us at this point, right? Which is just the variance of y sub 1. And that's the end of that one. So that was it. Two simple little proofs, but they're worth doing, and I think they're good little proofs. Okay, so the last example's got a lot of parts to it, but none of them are overly difficult. Okay, so the random variables y sub 1 and y sub 2 are such that the expected value of y sub 1 equals 4, expected value of y sub 2 equals -1, the variance of y sub 1 is equal to 2, and the variance of y sub 2 equals 8. So part A asks, what is the covariance of y sub 1 with itself? Assuming that the means and the variances are correct as given, is it possible that the covariance of y sub 1 and y sub 2 equals 7? And then they gave us a hint that if the covariance of y sub 1 and y sub 2 equals 7, what is the value of rho? In other words, what's the correlation coefficient? C, assuming that the means and variances are correct, what is the largest possible value that the covariance can take? If the covariance achieves this largest value, what does that imply about the relationship between y sub 1 and y sub 2? And then D is kind of a similar question, except for it asks what's the smallest possible value that the covariance can take, and if it achieves that status, then what would the relationship between y sub 1 and y sub 2 be there? So again, none of these require a lot of work, but it recalls us remembering the relationship between the covariance and the correlation coefficient on some parts. So part A was asking us, what was the covariance of y sub 1 and y sub 2? Or y sub 1 with itself, sorry. Covariance of y sub 1 times y and y sub 1. Well, according to the rules, that's the expected value of y sub 1 times y sub 1 minus the expected value of y sub 1 times the expected value of y sub 1, right? Which is just equal to the expected value of y sub 1 squared, if we simplify that first term, minus expected value of y sub 1 squared, because we got them times each other there, which is just the variance of y sub 1, which we kind of proved in the previous problem anyway, but according to the information given us at the beginning of the problem, that's just 2. So that's just knowing that the covariance of a variable and itself is always going to be equal to the variance of that thing. So in R, sometimes we can there's a covariance matrix, which I think we played around with a little bit in 3440 if you took me for that. But the diagonals of the covariance matrix are the variances for each of the independent variables in a data set. So this kind of goes back to that. Part B had asked us, assuming the means and variances are correct as given, is it possible for the covariance of y1 and y sub 2 to equal 7? So that was the question, right? Can it equal 7? No, it can't. It's not possible, and here's why. So the answer to this is no, but this is because the value of rho, which they were trying to get us to talk about the correlation coefficient, is equal to the covariance of y sub 1 and y sub 2 divided by sigma sub 1 sigma sub 2. In this case, if the covariance of y sub 1 and y sub 2 equaled 7, then in the denominator, based off the information given us, we have the variances so we can find the standard deviations. The variance for y sub 1 was 2, so the square root of 2 would be the standard deviation for that, and it was 8. The variance for y sub 2 was 8, so the square root of 8 would give us the standard deviation. This turns out to be 7/4, which is greater than 1. Recall the correlation coefficient has to be a value between and including -1 to 1. So you can't be larger than 1, you can't be smaller than -1. That's what I'm going to write here. And rho has to be between -1 and +1. So that's really the reason right there, and just using the correlation coefficient formula and plugging in the things we know, we could prove that that's not possible. So we can't be as big as 7 for our covariance. So what is the largest value? That's what C is asking us. Well, since the largest value that rho can take on is +1, if we take the covariance formula and say 1 equals the covariance of y sub 1, y sub 2 divided by, we kind of already see that in the previous problem that the sigma 1 times sigma 2 it turned out to be 4. So I'm just going to put a 4 down here. All right. This implies that the covariance of y sub 1, y sub 2 cannot be any larger than 4 if we multiply that and solve for the covariance in that equation. Which implies that the biggest value the covariance can take on is 4, and 4 over 4 does give us 1 if we plug back into the original formula for rho, which is, and what that means to us when the relationship between y sub 1 and y sub 2 is we have a perfect positive linear relationship. In other words, it's so strong we get one of those straight lines if we graph the points of the data set that would come out of this. Part D just did the opposite, except for we're looking for the lowest value a row can take on, and so that will help us determine what the covariance of is there, but it's a similar scenario. So the covariance of y sub 1 and y sub 2 divided by 4 is what we would have, similar setup. And this implies that the smallest value the covariance of y sub 1 and y sub 2 can be is equal to -4. And because -4 over 4 is -1 for rho, so rho equals, I guess that's what I should put there, rho equals, now it looks like a p. I don't like the variable rho myself for this, but this just implies that we have a perfect negative linear relationship between y sub 1 and y sub 2. So definitely dependent in both with both those scenarios. So anywho, that is it for that. I hope everything made sense today, and I hope everybody's doing well, and we'll talk to you on the next one.